Welcome back, everybody. We are in our home stretch. We've got, let's see, 4 more lessons, 4 more of these videos you've got to sit through until we're done. We got another quiz coming up, our last quiz coming up at the end of this week. Hopefully you've already taken a peek at the study guide. And then got a final next week, and that's it. So it's the home stretch, right? Don't fall apart on me, we're almost there. All right, so what we're looking at today are some properties of logarithms and how we can use those to solve some more complex looking either log or exponential equations. Now remember that logarithms are just exponents. Logarithms are exponents or powers. So if we were looking at the log base 3 of 9, we know the log base 3 of 9 is 2 because we're just looking for what power of 3 makes 9, and that's 2. So because 2 is the power of 3 that makes 9. So when we're looking for a log, we're looking for a power, right? So since it's just a power, since it's just an exponent, then the same rules that apply to exponents, they apply to logs. They just look a little different. Now you probably remember our product rule with our exponent rule that has to deal with product. So if you're multiplying something like x to the 4th and x to the 3rd, hopefully you remember that that is equivalent to x to the 7th power, that when we're multiplying those terms with like bases, we add the exponents. So our multiply rule says to add the exponents, right? Those two operations are linked. That's going to be true with logarithms as well. The quotient rule, when you're dividing those terms with like bases, we subtract the exponents. So we have x to the 10th divided by x squared, that gives us x to the 8th power. So we have division linked with subtraction. The same will be true with logarithms. And then the power rules, if we're raising a power to a power, we multiply those exponents. So x to the 5th to the 6th becomes x to the 30th power. So we have a power and a multiplication being linked, okay? So in the same way these things are linked here, they're going to be linked with logarithms because logarithms are powers, all right? So let me show you how they work. The product rule, when we're looking at it with logarithms, says something like this. If we have the log, let's say base a of some product, mn, that we can separate that product, that multiplication, using addition. So this would be equivalent to the log base a of m added to the log base a of n. Okay, so if we have the log of a product, we can expand that into the sum of two logs. So let me show you with a concrete example for a second. And it works both ways. We can take a product and expand it with addition, or we can take the sum and condense it with a product. Okay, so let me show you again with a concrete example. Let's say we had log base 2 of 4 and we were adding log base 2 of 8. Hopefully these are things we could evaluate, right? Log base 2 of 4 is 2 to what power makes 4? Well, that's going to be equal to 2. And log base 2 of 8, well, 2 to what power makes 8? Well, that's going to be 3. And if we added 2 and 3, we see that this expression is just equal to 5. Okay, so according to this rule, we could also say that this sum of these two logs with the same base can be rewritten as one log, the same base of the product. So the sum we can condense with the product. Instead of adding the two logs with the 4 and 8 as arguments here, we're going to multiply the 4 and the 8. Multiply the 4 and the 8. And what happens when you multiply 4 and 8? You get 32. So this is saying this would be equivalent to log base 2 of 32. Well, 2 to what power is 32? That is the 5th power, also equal to 5. All right, so just some verification that these two things are equal. So you can, again, do two things here. When we are going from a sum to a product, we call that condensing. And if we were working the other way, if we take the product and we wanted to separate it out into a sum, we call that expanding, okay? So we want to be able to expand or condense, really whatever is going to work in our favor. So let's look here. If we had the log base, this is just rewriting, there's really no purpose to this but to get comfortable with the property. We'll see how to use it to solve in a few minutes. But if we had the log base 3 of 5 multiplied by x, we could expand that and say this would be equivalent to log base 3 of 5 plus the log base 3 of x. So instead of multiplying these two, we can separate into two logs being added. And notice the base is the same for both. Okay, same thing here. This is going to be expanded into the log base x of y plus the log base x of z. And then here we're going in reverse. It's already expanded. So if we have the sum of two logs with the same base, we can condense that with a product. So we can make this 1 log base a of 4y. And just so that it's clear those two pieces are together, we're going to put them in parentheses. Okay, same thing here. We already have it expanded with addition, so we're going to condense it with the product. We're going to make this 1 log of 12w. Notice the log doesn't have a base. Remember what it means? Okay, that's the common log. If we don't see a base there, remember that's a log base 10. So just so you can remember, this is log base 10 of 12w. Let me get rid of that. That was just for you to recall. Natural log is a log. It's just another variation of a log, so it has the same properties. So we can condense this, make it 1 natural log of 4 times k. And again, here would be an example of where it might be useful to condense. So the log base 6 of 12 doesn't have an exact power. I can't raise 6 to a power, make it 12. Log base 6 of 3 doesn't have an exact power. I can't raise 6 to something and get 3. But if I condense this, if I make this 1 log base 6 of the product, what is 12 times 3? Well, it's 36. Now this has an exact value. 6 squared makes 36, which means this thing has a value of 2. Okay? And that's not the only useful place for that. We'll see some more uses in the solving. All right, let's try this now with the quotient rule. So the quotient rule, remember, was linking our division and subtraction. That's what we have linked here. If we have 1 log of, which way did I go here? 1 log base, let's just say base a of a quotient, m divided by n. I could expand that and say it's log base a of m minus log base a of n. Okay, so again, multiplication we expand with addition. Division we're going to expand with subtraction, or if we had to condense, we condense addition with multiplication. We will condense the subtraction with division. So here, this is going to be equivalent to the 1 log base 5 of 2 divided by x is equivalent to log base 5 of 2 minus the log base 5 of x. And here, this would be equivalent to log base z of x minus log base z of y. And notice the numerator comes first, the denominator is what we subtract. Okay, this would be equivalent to, now we're going to have to go the other direction. We already have this expanded out with subtraction, so we're going to condense this to 1 log base b of w divided by 7. And I prefer the parentheses there. Here, already expanded, so we're going to make this 1 log of 5 divided by m. And here, we're going to make this 1 natural log of p divided by 8. And then here's another one where it's kind of useful. There's no power of 8 that makes 192, and there's no power of 8 that makes 3. But if I condense this, I have 1 log base 8 of 192 divided by 3 is 64. And that can be evaluated, because 8 squared makes 64. This thing has a value of 2. Okay, one last rule, and then I'll show you how we can use this to solve. So the power rule, remember the power rule was linking a power with multiplication. That's what's going to happen here. If we have 1 log base a of m to the nth power, then this is going to be equivalent to n times the log base a of m. So if you have a log to a power, the power becomes a product, or we could think about it as multiplying, comes down in front to multiply. The power becomes a product. All right, so again, we can expand or condense, although not one doesn't look any shorter than the other. This would be equivalent to, I guess I should turn the pen on. This would be equivalent to 2 times the log base 4 of x. So this power comes down as a product. Okay, or this would be equivalent to p times the log base q of 3. And then in reverse, we already have a product here, 3 times natural log of z. This product can come up as a power. So this would be the natural log of z cubed. And z cubed, right? Not the natural log of z cubed, but the z gets cubed. Okay? So these properties we can use to solve. We're going to use them to solve something that looks like that mess, right? If we have a bunch of logs in our equation, we want to try to condense them down to 1. So when an equation contains more than one log, we're going to use the properties to condense. If we can condense down to 1 log, then we can rewrite. And once we have it rewritten, it really is going to look like what we were doing the other day. Now just remember, and this again will make a little more sense when we look at the functions, but we can't take the log or natural log of negative numbers or 0. And so if we get a solution that produces a negative or a 0 when we plug it back in, it's going to be an extraneous solution. And then I'll leave those other 2 bullets until we get down a little further. Okay, so let's look at number 1. We're going to try to use a property here to make this something that's manageable. So 2 logs, same base, separated by addition. We can condense that with multiplication. So we're going to rewrite this as 1 log base 4 of 5 is going to be multiplied by, I'm going to use a bracket here, 5 is going to be multiplied by x plus 2. And it's still equal to 3. Okay, so I didn't change the equal, didn't change the 3, I just condensed, right? Since there's addition, I condensed with multiplication. So now we have something that we can rewrite. We could rewrite this now as the base of 4 to the 3rd power, 4 to the 3rd power. It has to equal 5 times x plus 2, the argument. So 4 cubed is 64, and then if we distribute here, we have 5x plus 10. We can subtract the 10 from both sides, so that 5x is equal to 54. Oops, so I swear I went back to red. So 5x is equal to 54, and now we can divide both sides by 5. That cancels, and we have it. X is equal to 54 divided by 5. Okay, now if you wanted to check your answer, I wouldn't do it every time, but maybe if you're taking a quiz and you're unsure, we have the log base 4 of 5, and we're going to add the log base 4 of 54 fifths plus 2, and when I type that 2 in there, better give me a 3, and it does. Okay, so it's confirmed that my 54 over 5 works. Alright, here's another one. Same concept, but this time we have 2 logs that are separated with subtraction. So we're going to condense this one with division. So just make a note here. That's condensed with, oh my, don't mind my lack of spelling abilities. When it's addition, we condense with multiplication. And when it is subtraction, we're going to condense with division. Okay, so this becomes 1 log base 2 of 7x minus 3 gets divided by 3 and still equal to 4. All right, then once we have it as 1 log, we can rewrite it. So it's 2 to the 4th power. 2 to the 4th power equals the argument, which was 7x minus 3 over 3. Now 2 to the 4th power, that's 16. And I'm going to make it 16 over 1. That way I have a fraction equal to a fraction, and I know what to do. I can cross multiply. So 7x minus 3 times 1 is going to give me 7x minus 3. And 16 times 3 is going to give me 48. Now I can add the 3 to both sides. That cancels. And this is going to come up here. And that leaves me with 7x equal to 51 And now I can divide both sides by 7. That cancels, and x is going to equal 51/7. And again, if you wanted to plug it in and check it, you could, but it's going to work. Okay? All right, number 3. Natural logs work the same as common logs, same properties. They just look a little different. So again, we have multiplication here, so we're going to condense that with, we have addition here, so we're going to condense with multiplication. So we're going to make this 1 natural log of 2 times x will just be 2x, still equal to 5. And now we can rewrite this. Remember, there's a little invisible base e there. So we're going to say this is e to the 5th power, equal to the argument, which was 2x. And this one's pretty easy to solve. If we want to get x by itself, all we have to do is divide over the 2. So divide 2, that cancels. So x is going to be exactly e to the 5th over 2, which is approximately, let's find out, e, where are you, e to the 5th power, and that's going to be, nope, not there, divide by 2, 74.21-ish, 74.21. Okay, and again, if you wanted to plug it back in to check it, you're not going to have an exact, if you want to plug in the decimal, it's going to give you approximately 5 back. If you want to plug in the e to the 5th over 2, you'll get the exact 5 back. All right, looking at number 4, notice the logs are not on the same side of the equation. So the first thing I would do is move that log base 4 of x over. Log base 4 of x plus 6 can stay where it is. This guy, I'm going to subtract to the other side. So it becomes a minus log base 4 of x equal to 2 here. And then I can condense that subtraction with division. So we're going to make this 1 log base 4 of x plus 6 over x equal to 2. And now I can rewrite. And so I ended up with the 16 again. When I rewrite this, this is 4 squared equal to the argument, x plus 6 over x. So again, this 4 squared is 16. I'm going to put it over 1. That way I have a fraction equal to a fraction, and then I can cross multiply. So multiplying here by 1 means I still have an x plus 6, and multiplying 16 times x gets me 16x on this side. So I'm going to subtract x from both sides. That gets me 6 equal to 15x, and then I'm going to divide both sides by 15, and that will cancel that, and so x is going to equal, 15 doesn't divide into 6, but that does reduce. 3 is going to go into 6 twice, and into 15 5 times, so 2/5 is going to be my answer. Okay, so far so good. All right, now number 5 looks, I don't know, it looks a little different to me. I don't know if you can see the difference. So at number 4, maybe similar to number 4 where the logs aren't on both sides, but when I subtracted the log base 4 of x over to the other side, I still had a constant on the other side. If I move this one over, I'd get a 0 there, which makes this a little bit different. Not that I couldn't do the same thing. I could subtract it over and leave the 0 there, and then I'd have something raised to the power of 0, but this one is simpler. This one kind of goes back to how we started this unit. Remember we said if I had like 6 to some power here and 6 to some other power here, if those bases were the same, that they would cancel and the exponents would have to be equal. It's really the same concept we have going here. If I have the log base 6 of something equal to the log base 6 of something, don't those somethings have to be equal? Absolutely, right? So if I have a log, 2 logs the same base, a log equal to a log, and nothing else, like no plus 2, right, or minus 4, no other pieces in the equation, just a log equal to a log, we can literally just cancel those logs out. So these logs will cancel, and we're going to make the 2x minus 3 equal to the 5x plus 12. And that would be true for natural logs too. If it was like natural log of x equal to natural log of 5x minus 1, right? If that's all we had, logs and nothing else, those logs would cancel, we make that equal to that, and we solve, okay? So, I think that was a bullet I left blank, yep. When the equation contains a log equal to a log, or natural log equal to natural log, and nothing else, then the logs cancel out. They cancel out. Okay, so we can continue here. Let's get the x's together. If we subtract these two over, that's going to leave us negative 3 equal to 3x plus 12. Let's get rid of the 12. That cancels. And so 3x is going to be equal to negative 15. Now if I divide by 3, then, oops, those cancel. And I have x equal to a negative 5. Now, we didn't have this issue occurring anywhere else, but if we put in a negative 5, let me just, so you can see it here. If I put in a negative 5, now I know that it's going to create the same thing on both sides, but if I try to take the log base 6 of, let's say 2 times negative 5, and then I subtract 3, it's going to say undefined. So I'm trying to take the log base 6 of, when I plug negative 5 here, I get negative 13. When I raise 6 to some power here, it's never going to be a negative number. Whatever I raise 6 to a power of, whether it's 0, I get a 1. If it's something negative, I'm going to get a fraction. And if it's something positive, then I get some big number here. There's no way I can raise 6 to a power and make it a negative number. So even though it makes both sides of the equation equal, this is an extraneous solution because we can't take the log of a negative. So this is extraneous. Didn't do anything wrong, just got an extraneous solution. So if the one solution we have doesn't work, what does that mean about this equation? It means there is no solution. Okay, so that kind of stinks, but it happens. All right, now, I think so far all of those were pretty manageable. Here's the one that is definitely different from the others. Now, all of the other equations were log equations, where we were using the properties to fix the log equation, then rewrite in exponential form. Here we have to go in reverse. We start with an exponential equation. We're going to have to use logs to fix it. Now, we've solved some log equations before. If I had not a 7 to the x here, but let's say just a 7 on this side to the x plus 1, I could just rewrite this. This would be log base 3 of 7 equals x plus 1. I subtract the 1 over, and I call it a day. But I can't do that here because the 7 has a power of x, right? That's no good here. So what, right? What do I do with this situation? I don't want my variable to be on both sides like this. So this is where that third property that we haven't used yet comes in handy. So the property that says if we have the log base x of y to the z power, that power can just come down as a product. We can actually use logs in solving. So in the same way that we like add 1 to both sides of the equation, or divide both sides of an equation by 2, we can take the log of both sides of an equation. So why would we do that? Let me show you. I'm going to take, and log and natural log work the same way, so I'm going to use natural log here just because it's less to write than common log. But if I took the natural log of 7 to the x power, and I took the natural log of 3 to the x plus 1 power, okay, just take the natural log of both sides. That's a legal move. It's like doing anything else to both sides of the equation. Well, now I have a log to a power. So this power can come down. So we can call this x times the natural log of 7. Oops. And let me make sure my colors match up here. And again, this power can come down. So we can call this x plus 1 times the natural log of 3 would be left there. Okay, so how is this helpful? Colors, here we go. Well, natural log of 7 and natural log of 3 are just some decimal amount, okay? So on this side, I'm going to leave this alone. X times the natural log of 7, I'm just going to leave that alone for a second. Here, I'm going to distribute this. X times natural log of 3 is going to be x natural log of 3. That's just some decimal times x. And then 1 times natural log of 3. So plus 1 times natural log of 3 is just a natural log of 3. Anything with an x I want on the same side of the equation, anything without on the other side of the equation. We've seen a similar concept to that before. So what I'm going to do is I'm going to subtract this term to the other side. So that gives me x natural log of 7 minus x natural log of 3, and then I still have the natural log of 3 here, right? This just came down. Okay, now why do I want both terms with an x on the same side of the equation? Well, because if we have an x in common, we can factor that x out. So now I'm going to factor out the x they have in common. And if I take away the x from factor out, divide it out from both those terms, then just the natural log of 7 and the minus and the natural log of 3 would be left. On the other side, I still have this natural log of 3. Now I can solve for x, right? X is being multiplied by some crazy decimal in the parentheses, so I'm going to divide that crazy decimal over. So I'm going to divide both sides by this natural log 7 minus natural log 3. Do it here. Natural log 7 minus natural log 3. And that cancels it from this side. So x is going to be equal to, oh, I do have space there. So x is going to be equal to the natural log of 3 divided by the natural log of 7 minus the natural log of 3. That is the exact answer. Approximately how much is that? Let's find out. I know that is ridiculous, right? Let's make a fraction. We're going to put natural log of 3 on the top, and then natural log of 7 minus, minus natural log of 3, and there it is, about 1.297, about 1.297, okay? Now, in my opinion, this work is ridiculous. We're not going to see, fortunately, a lot of equations. Let me just distinguish these. This is the exact answer. This is the approximate answer. The exact answer, I would say if you're going to move on to some higher levels of math, this is definitely work you should be able to do. You have to realize that, again, just like you can add 1 to both sides of an equation or divide both sides of an equation by 2, you can take the natural log of both sides of an equation. And we would do that if we were trying to solve for an exponent. Now, we could have used this process in all the other exponential equations we solve. It just seems ridiculous to do all that work when we don't have to. But we had to use it here because I couldn't make both sides have the same base, right? Like if I had 6 to the x equal to 36, well, that's not an issue because I can make this 6 squared and get those to cancel. That wasn't going to be an option here. And because I had exponents on both sides, I couldn't just rewrite it in log form. So there are cases like this one where taking the log or natural log of both sides is the only way to get to that exact answer. Now, if all you needed was an approximate answer, Desmos could avoid all of this work for you, and I just want to show you, because I can, right? This Desmos can do for you. If you put each side of the equation in as a separate function, so one side of the equation is 7 to the x power, and put the other side in, 3 raised to the x plus 1 power, you want to know where these two things are going to be equal. So what you're going to do is find where they cross on a graph. And that point right there, the x value, right, we're trying to solve this equation for x, the x value and the point where they cross is the same solution that we just got here, 1.296, which we rounded, 66, we rounded to 7, okay? So if you graph each side of the equation and find the point where the two graphs intersect, the x value in the solution is, the x value in that point of intersection is the solution to your equation. So if you needed the exact answer, the only way to get it is using logs. If you needed the approximate answer, then you could graph in Desmos and find the intersection. Let me clarify here. So you could graph in Desmos, and the intersection, oh, I can't fit that there. The intersection would show the solution. Would show the solution. Okay? So if you needed the approximate answer, then I would definitely avoid all that work. All right? And that was, again, a pretty crazy one. I don't expect one of those to be on your